Hey guys, we're gonna watch the notes video, Is Yawning Contagious? Okay, so we started out with a kind of diagnosing or looking at the experiment that they did. They split them in groups, and we're doing this. We're comparing these results here, right? So we analyzed that there was a difference and that there was some amount of evidence that the second group that was seated did. But some groups agreed that, yes, there is a difference. And some groups said, well, that's a difference, but it's not really a very big difference, right? So as we analyzed it more, we laid out this idea of the null hypothesis and that our alternate hypothesis would be what we think. We think that yawning is contagious, but we have to set the null hypothesis is that it's not, and then prove that it is, if that makes sense. Okay. So here's some data. The other group, if you see this little one, this was data from period 7. And then in period 6, this is data. So this is actually both pieces of data. And this was the p-value we got together as a group. And in both groups, we busted the Mythbusters. So what is this actually saying? What this is saying is that that's a very, very high p-value. It's saying assuming H sub O is true, which is assuming that yawning is not contagious, there is a 0.59 probability of getting a difference in proportion of 0.04 or greater. So that's a very high likelihood. So because this number is way bigger than 0.05, we do not have convincing evidence to support our H sub A. What is our H sub A? It's that yawning is contagious. This means that we failed to reject the null. We failed to show that yawning wasn't contagious. Okay. Now, in these chapters, the hardest thing is oftentimes stumbling over the words, like the yawning is not contagious, like the double negatives can be pretty difficult. So let's break this down. I'm going to show you the notes. And again, I think some classes got the notes, some didn't. Some people had to leave early. So we'll just walk through again, learning target 1. Our hypotheses is that there is no difference between the two groups, right? Or said another way, that they're exactly the same. Now, there's some ways in this problem we believed that the first group, since it was seated, would be more contagious, right? We could have done the study and seated the second group. Then if we seated the second group, we'd have reason to believe that the second group should be bigger. And as you'll see in another example, sometimes we want to set our alternate hypothesis, A for alternate hypothesis, as merely that they're just not equal to each other. Maybe one's higher or one's lower, but they're not equal to each other. So this is common in when we compare men and women, okay? So maybe you're trying to discover, are men more emotional or women more emotional, right? What proportion of men cried when I showed a movie versus men and women? We should assume that they would cry the same amount from the same shocking movie, but we might have an alternate hypothesis that they behave differently. Maybe one group over another, but you don't know. Again, depending on who was in the movie, right? Or if it was a male actor in the movie, maybe the men would empathize with the man at seeing themselves in that setting, right? So that would be a perfect example of why we would want that as our alternate hypothesis. Okay. So what is learning target 2? Well, now that you have two groups, then you still need to take random samples of men and women. Or if you're going to do something like in an experiment, you can't take random samples. You have to take volunteers. So volunteers are not random. They chose to be in the group. So therefore, you must randomly assign to show them. Okay? And this allows us to show causation. Okay, so it looks like this is I got ahead of myself. Causation. Is it causation? Okay, so if that happens, violent movies cause women to cry more. I can actually say causation if I set up an experiment, and that experiment, each group was randomly assigned to a different group, okay? The second condition we have to maintain is that you need to make sure that your group of men is bigger than the population of men and your group of women is bigger than the population of women. That's what we mean there. And again, most typically, those conditions are met. We check this when we're sampling without replacement. And most of the time we are sampling. So if we picked 20 women to be in this study, and there's lots of women, right? And so that's not a problem, but we're not replacing each woman each time it was picked, or else that would mean that a person could be picked twice. We're definitely sampling without replacement. Therefore, we need to make sure this condition is met. Okay. Lastly, and this one's the one that's very different. This isn't like anything else we've done in previous chapters. So we definitely want to think about maybe putting a star here. This is kind of new stuff. Normal calculation. We must abide by large counts, but notice what's happening here. I take my number of women, let's say, but I don't multiply by the proportion of women. I multiply by the combined, because remember, we're assuming men and women are the same. So I would just put the number of women and the number of men and combine them. So if I talk to like 200 women and maybe 210 men, then I combine that proportion at 410. And then if 130 women cried and 120 men cried, then I notice I'm going to combine those and create this P hat combined. This should make sense because it is as if we're shuffling the cards together in a single pile. We're ignoring that they're men and women, and maybe it's just, your different background, your natural personality. People cry. Different people cry at different things. Some people don't cry or cry very infrequently, and vice versa. So this is why we are combining our P hat when we do our normal calculation, because our H sub O is we're assuming they are the same. Now let's dig a little deeper in this Mythbuster. Taking this data, how would we have done it if we tried to get a badge? So if we wanted to get a badge, we would calculate. So it looks like a total of 10, right? This 10 yawned out of a total of 34. And 4 yawned out of a total of 16. So that's the proportion of each group who yawned. This was group 1, right? And this was group 2. If you don't remember going back here, these group 1 was seated to yawn. Group 2 was not seated to yawn, okay? So we combine them because our H sub O is we are to assume that they are exactly the same. So this is the equivalent of shuffling the cards. Now all 50 cards are in the deck, all right? We're combining those numbers on top as well. And again, they give us this outcome, P combined. We use this P combined to do our normal calculation. So that's where this number is coming from. Okay? In the first group, I talked to 34 people in group 1, and we talked to 16 people in group 2. And notice that could have been another thing that went wrong with the show. It looked like they didn't put enough people in there. All right. What else? Well, you still also have to do into 1 minus P hat. That has to be greater than 10. So analyzing this, 16 times 0.72. And yes, that number is greater than 10. So those are fine, but these are not fine. So that's why we stop there in the notes and don't proceed with a conclusion, because the conditions in this situation were not met. All right. So it looks like we got our elements, state, plan, and we stopped. We didn't keep going with the do and conclude because we didn't meet the conditions. But let's think here before we move on. When I go to do my randomness, right, we did use random assignment. And we did this so we can show causation. Okay, what about 2? Well, our 10% condition here, we didn't have sampling, so we don't need to check this, right? We didn't take a sample. We did not. Now, let's say you did it anyway, they're not going to count off. So some kids just automatically do it, right? In fear of what if it's the time that I should have done it, but I didn't realize that I should have done it. All right. So what is our next activity? Okay. I'd like to put this again on video so it allows you a chance to kind of like see each element and be able to watch this video multiple times if you think that you need to. Okay. So reading it, it says, the student council at a large high school is wondering if juniors or seniors are more likely to attend prom. They take a random sample. Oh, we like that, right? They take a random sample of 50 juniors and 28 and find that 28 are planning to go to prom. And out of the 45 seniors, 29 are planning to attend. Okay. So let's walk through this. Our parameter is P1 minus P2. And what do those stand for? Well, those would be the true difference in proportion of juniors and seniors planning on attending prom. All right. Well, again, we have to first assume that they're the same. So if they're the same, there is no difference. And what do we alternatively want to believe? Well, it says, do you have convincing data that a higher proportion of seniors are going to prom? Okay. So I probably, I kind of like it this way because I think this is what my calculator. So if I'm going to call the first group junior, then we think maybe seniors are nostalgic, probably more likely to go to prom. So what would that mean? If I take the first one and it's smaller minus the second one, then I'm assuming a number that is negative or less than 0. What is the name of the procedure we're using? This is called a 2-sample z-test for P1 minus P2. So instead of just P, I'm really trying to find a difference between the two. What is my statistic? Well, we've got P1 hat minus P2 hat, right? So we've got 28 over 50 minus 29 over 45. That gives us 0.08. Okay, and they've set it at a 5% level. So this is still 5% like it normally is. Now let's dive into checking these conditions, okay? So 1, we want to check for randomness, and we noticed that they took random samples, and we also want them independent of one another, right? We don't want one influencing the other. So independent random samples. All right, and 2. I'm going to say our 10% condition is met. And the reason why is I'm going to say 50 is less than 10% of all juniors at this school. And let's hope that's true because we want to keep going, right? and that 45 is less than 10% of all seniors at that school, right? And the last one, but definitely not least, how do we know that we can use normal calculation? Well, that's because of large counts. So large counts tells us that we have, how many people do we talk to? Yeah, 50 people in group 1. And I got to do N1 times P hat combined. Okay, so let's combine these. So P hat combined would be 28 and 29 for a total of, what is that, 57? And out of, I talked to a total of 95. So P hat combined would be, I don't have a calculator. Where's my calculator? I know, you guys have a calculator. Where is that? I didn't write down that calculation. Sorry, guys. So I wrote down, though, that N1 times 50 times P hat combined was 30. So this must have been 0.6. Okay. And then 1 minus P hat combined would be 0.4. So 50 times 0.4 would be 20. Now we have to check in the second one, right? In 2 times P hat combined. So that was 45 people times 0.6 and 45 people times 1 minus P combined hat, which would be 0.4. And we get 27 and 18. So all these numbers are less than 10. Or excuse me, greater than or equal to 10, which we like. So we're good there. All right, so our conditions have been met. And now we're ready. So what is the mean? If we think about what would be the middle of this graph, it would be that it would float at 0. So what does that mean? Well, it would essentially, we're saying that the mean of my proportions should be the subtraction between these two. Assuming they're the same, it should just equal to the subtraction of the two, or be 0. Okay? What is the standard deviation? Oh, oopsies, they asked for my picture over here. So, okay. What is my standard deviation? Well, my standard deviation, when I combined P hats, would be right? That, now that I'm combining, and again, this is N1 and N2. And so what do we get there? That would be, I'm going to have to go over here. P hat combines 0.6 times 0.4 over 50 plus 0.6 times 0.4 over 45. Take the square root of the whole thing, and we get 0.101. Okay. All right. And what did we end up getting? So our test statistic was this. So we're trying to figure out, well, that's where our P hat would go, right? Our difference of our P hats. And so that's negative 0.08. So we're trying to find the area under the curve to find what would be the probability of that outcome if we do, in fact, presume that there isn't a difference between these two groups. So what is the generic formula that makes this normal curve work? Well, if we think about it, it's we wrote it in our notes the last class. We take our test statistic, like a z-value, right? And then we take our statistic, subtract it from our parameter, and we put all that over the S, the standard deviation. So this is kind of this formula AP statistics. what was our actual value? Well, the actual value we got was P1 hat minus P2 hat, right? And what did we think we get? Well, we're supposed to think that we're not going to get a difference. So that's going to be 0. Okay, and then we took it all over our standard deviation, which is this big old yucky formula right here, right? So that was P hat combined times 1 minus P hat combined over N1 plus P combined, 1 minus P combined over N2. Took the square root of the whole thing. So if we type this in our calculator, we get the negative 0.08 minus 0, right? That's no difference between the two. And our standard deviation we already got was this value. So our calculator comes up with this 0.79. When we go to our table A, so that's our test statistic, or you could think of this as our z value, 0.79. We can go to table A and find that our p-value is 0.2148. Like, oops, that's not what we want, right? So what does this mean for us? Well, we must always assume that our null hypothesis is true. So assuming, which is what the calculations are based on, assuming that the null, which is P1 minus P2, is 0, that there is no difference, we found mathematically that there is a 0.2148 probability of getting this outcome. What outcome did we get? We got a difference of negative 0.08 or lower purely by chance. And the reason we did that was because 0.2145 is greater than that. We failed to reject the null. All right. We do not have convincing evidence of Abe's survey. So what is Abe's survey again? What were we trying to prove? Well, we were trying to prove we don't have convincing evidence. We don't have convincing evidence that a higher proportion of seniors are going to the prom than juniors. So again, what I try to tell you guys is it looks like I come out with these words out of nowhere, but I really am just copying them out of the problem. So that's how I'm going to finish my sentence, and I'm even too lazy to write it out. I'm going to just copy it in. So assuming the null is true, there is a 0.21 probability of getting that value or lower purely by chance. So because this value is greater than 0.05, we fail to reject the null. We do not have convincing evidence. We do not have convincing evidence that a higher proportion of seniors are going to the prom than juniors. Period. Oh, we could say at the 5% level. Nice work, guys. See you in class. We'll actually pick up class right here on this page. See you next time.